The base. Remember, we have a base in this reaction. We do not have a nucleophile, as it's not a substitution reaction. So the base appears in the rate equation, as we can see right here in the rate equation. So its concentration and its strength, of course, will have an impact on the reaction rate. The stronger it is, the faster the rate. E2 requires obviously a strong base, so a strong base is a charged base. Although, just to warn you, remember we can have charged species that can be strong nucleophiles, but not necessarily strong bases. E2 reaction can be generally run with negatively charged bases like OH minus. OH minus, like right there. OR, which could be an example of ethoxide, like we've seen before. Remember, by the way, get used to it, sometimes written like this, OET minus. This one just keeps moving. Or, of course, OCH3. OME as well. So all of those are strong bases, but you can also have strong bases that are bulky, sterically hindered bases, huge bases. They have too much sterics. And these are examples, DBN, which has the following name right here, or DBU. So be aware of these two bases. If you see them, then you know you have an E2 reaction right away. It's noteworthy to mention, of course, a very common base, which is T-butoxide or tert-butoxide, I mean. So it's this bulky base. You are aware of it. It's a very common base used in organic chemistry. It's a bulky base. It's a bulky base. And a strong base as well. Sometimes it's written, of course, it's with K as a spectator ion. You would see it as TERT or T, BU, OK, or sometimes BUTOK. But right? These are common. These are very common, again, bases used in organic chemistry. Again, just look at the structure of the base. Sometimes, by the way, it's drawn like this. Again, we are aware of all of this. Look at the structure of the base and judge whether it's bulky or not by how big it is. The solvent is aprotic. If it's available, there's a caveat here. Polar aprotic solvents are necessary, or they're helpful because they do not solvate the base very well, which of course enable it to attack the proton. So you can go back to the SN2 reaction, why polar aprotic solvents are useful. It's because, again, they do not shield that nucleophile, or in this case, the base, from removing the proton. So you want them to have ease at removing the proton. You don't want too much hydrogen bonding, which kind of like shackles those bases and doesn't let them freely remove a proton. And Zaitsev's rule is a very important rule. It explains something called regioselectivity, which means which atom you are choosing to make a bond or break a bond. Regio, like from a region in the molecule. So here is our base. And here is the alkyl halide. Zaitsev's rule states that the resulting alkene product is the most substituted, most stable, of course, product achieved by removing a proton from the more, or the most, in this case, substituted beta carbon. So just be aware that, once again, this more substitution you have R groups, the more stable. So this one would be more stable than, let's say, this one, because it has more R groups. Okay, so let's look at this example. It's going to get fuzzy a little bit here because we are going to draw here where the R, where the beta carbons, alpha carbons, and of course the beta hydrogens are. So in this case, you have C right here, this one in the middle, that's going to be your alpha carbon. And if you look, you actually have three beta carbons. You have one right there, you have one right there, and of course you have this one. Zaitsev's rule says when the reaction takes place, an elimination reaction takes place, make sure you remove the proton from the more substituted carbon, or in other words, the one with the least number of hydrogens. So Zaitsev's rule says, look at these beta carbons and remove the proton from the one that has the least number. So if we look at this one has 3 H's. This one also has 3 H's. And this one only 2 H's because there's a methyl. So if you'd like to pause and see that, go ahead, but this is critical. So Zaitsev's rule says remove the proton from the one with the least number of H's. And if you do that, you produce the more stable product. Okay, there's a mistake here. This is an H. Okay. This is my alpha carbon. This is my beta where it had the 2 H's from or at. I'll make that red. This would be makes about 69%, which is the more stable alkene. That doesn't mean that the other one doesn't take place, but we will solely focus or mainly focus on the one that's more stable. Of course, you would get also 31% of this one. This just keeps. Once again, here's my so if you look at this one now, here's your alpha. So you actually ended up removing it from one of these to one of these that has 3 H's on it, either this one or that one. So I'm going to mark, let's say, this one in red so you can see it. So this gives you about 31%. And of course, it's less stable. And the reason why is because, again, the whole idea is more stability. Now, what would I ask you? I may ask you in some questions to draw both the more stable and the less stable. But most of the time, it will be that you automatically produce the more stable alkene. Most of the time. But there might be a question where I'm asking you to draw the two possibilities and tell me which one would be more stable, which one would be less stable. We will work on this when we meet in class to ensure that we know where to remove a proton from. In some elimination reactions, the less stable alkene is the major product. And I know you might be saying, okay, it just took me time to establish this. Now you're saying backwards. Well, we cannot just lie, right, about the facts here. And the reason why is because when you have a hindered base with a hindered alkyl halide, then the less stable product will have to take place, or will have to be the major product. And if you look here, it's for a very obvious reasons, is if you look at these two, this is your alkyl halide right here. It's tertiary alkyl halide. And it's very hindered. It's very hindered. Meaning you have, it's just, there's so much around that alpha carbon here. So that's your alpha carbon, by the way. But you have three, of course, beta hydrogens. Like here, you have a beta hydrogen. Here you have a beta hydrogen. And of course, there you have a beta hydrogen. And if you look at the base as well, T-butoxide, it is also very hindered. It's a tertiary base as well. And it's very hindered. So what are you supposed to do? You're supposed to remove from the most accessible H, of course, one of those beta H's. So if you run the reaction, you would get actually this. And that would be your tri-substituted, which would be the more stable one, but you would only get 28% of the yield. But this one right here would be the less stable because it's only di-substituted. You would get 72%, meaning you did not remove the H from this one right here, according to, so this one violated Zayatev's rule because that they're both bulky, very bulky. So in this case, what we'd like to say is that the base removes the most accessible OH when the base and alkyl halide are very hindered. That's the key. So keep that in mind. Chemistry has, of course, exceptions, but make sure you understand what these exceptions mean.